In this section, 1.8, we're going to talk about derivatives and the rate of change. So first we'll talk about the average rate of change, which actually is not calculus-based. This is something we could have done in other math classes. So let's consider the function f of x equals x squared. And we want to know how much does our function change from x equals 2 to x equals 5. So here's x equals 2. Here's x equals 5. Better draw that a little more to scale. And we want to know how much does it change. So we went over 3, and how much did we go up? So if x is 2, then y would be 4, and if x is 5, y would be 9, right? Because f of x is y squared. So let's see. So f of 5 minus f of 2 is 5 squared is 25. So 5 squared minus 2 squared, or 25 minus 4 equals 21. So the function went up 25, or 21 units. But now we might ask you something like, well, what was the average rate of change? Because that was 3 units, but over a space of 3. So we went up 21, but we also went over 3. So we might want to know how much, kind of get the average, so about how much did it go up per 1 x unit. So y went up 21, and x went up 3. So if you want the average would be 21 divided by 3, or about 7. So our average rate of change would be for each additional x, y went up about 7. Now that is an average. Notice this isn't a constant slope through here. Sometimes we're going to be a little bit slower, and then we're going to go up faster. But if you took the average for each additional y went up about 7 over that interval. And so you can find an actual official formula for that. The average rate of change of f of x over the interval x equals a to x equals b is f of b minus f of a over b minus a. So that's what we did up above. We just didn't actually write it out like that. So our average rate of change equals f of b. So you plug in the b first, so the 5. So we do the 5 squared minus 2 squared over 5 minus 2, or 21 over 3 equals 7. So again, average rate of change is just kind of what was the slope, but you take the average over the entire period. But rather than looking at averages in calculus, we'll want to know how fast is it changing right at a single point x equals a. And to know how fast it's changing right at that point, we look at the derivative, x equals a, or f prime of a. So this tells us our rate of change at that one specific point. And that's why it's called the instantaneous rate of change is just equal to your derivative. So again, we've talked about this quite a few times. Our derivative tells us our slope, or it tells us how fast we're changing right at that one point. So in example 3, once again we have this parabola. Here's x equals 3. And we want to know what is the slope right at that point. How fast is it changing right there? Not an average over a big interval, but right at that one point. So to do that, you first take the derivative. So if we have x squared, you bring down the 2, x, drop your power by 1, so you get 2x to the 1, or just 2x. So now plug in 3, so f prime at 3 is 2 times 3, or 6. So at x equals 3, we are changing at a rate of 6. Or at x equals 3, if x goes up 1, y goes up about 6. So notice our average up here was 7 because it was over the entire interval. But if you looked just at the 3, which would be right about here, right there, our slope is 6. So there are a few problems where we will ask you to find the average rate of change, but that's more of just to compare it. Usually in calculus we care about the instantaneous rate of change because we do know how to take derivatives. Okay, now applications for physics. Okay, so what we do is we start with our original function, which we'll call s of t, okay, which represents the position of a moving object at time t. So s of t, or our original, is the position. Okay, now how fast an object changes position, or in other words speed, could be considered the rate of change of the position. Right, so how fast your position changing, that's your speed. So our velocity is found by taking the derivative of our position function, s of t. And if you're in physics, acceleration is considered how fast your velocity changes. So acceleration is the derivative of velocity. So we've made a nice little table here, so you can keep track of that. You have position, velocity, and acceleration. Position is your original, which we'll call s of t. Velocity is v of t, acceleration is a of t. And if you want to get to velocity, you take the derivative of position. And if you want to get to acceleration, you can take the derivative of velocity, or you can just take the second derivative of your original position. So let's see what that actually looks like. Okay, a ball is thrown straight up in the air. The height of the ball position is s of t equals negative 16t squared plus 40t plus 6. So our ball's height goes up, reaches the top, and comes back down. Notice this isn't the path of the ball. They threw it straight up and straight down. This is height and time over here. So to take our derivative, or to find our velocity, we take our derivative of our position. So we're going to have negative 16, bring down your 2, t to the power of 1, plus 40, plus 0. So this is negative 32t plus 40. And our acceleration is found by just taking the derivative of that again. So derivative of negative 32t is negative 32. Derivative of 40 is just 0. So we get negative 32. Okay, and that acceleration is related to gravity. And so that's why all of these problems with throwing balls in the air will always have that same acceleration, because gravity is the same. So first, what is the height when the ball is released? Well, height, that's our position. And when the ball is released, that's just when time equals 0. So all we have to do is find s of 0. So negative 16 times 0 squared plus 40 times 0 plus 6 equals 6 feet. And that makes sense, because if you were to throw the ball, most people are about between 5 to 6 feet high, and when they release the ball, it's probably about 6 feet in the air. What is the velocity at 1 second? Well, we already found our velocity equation up above by taking the derivative of our height function. So all we have to do is plug 1 in. So negative 32 times 1 plus 40 equals 8. So 8 feet per second. And what is the velocity at 2 seconds? Well, just plug 2 in. So negative 32 times 2 plus 40 equals negative 24 feet per second. Negative. My negative didn't go in there. Okay, notice here that this is positive. So the positive means going up. This velocity is negative. So the negative means going down. Okay, so if you've taken another math class where they really talked about velocity and speed, it turns out that speed just kind of tells you how fast you're going. So it would just be 8 feet per second, 24 feet per second. You don't really care which direction you're going. But velocity comes with comes with the direction built in. So in this case, we have a positive 8, which means we're going up 8 feet per second. And a negative 24 means we're going down 24 feet per second. Okay. And what is the acceleration at 2 seconds? So a of 2, we just plug in 2 into our acceleration. But notice there are no t's in our acceleration. Our acceleration is negative 32 all the time. And acceleration is considered feet per second squared. Okay, and then I might ask something like, when is our velocity equal to 0? And what will this represent? So we know our velocity is equal to negative 32 t plus 40. And we want to see when is that equal to 0. So we'll set equal to 0, solve for t. So negative 32 plus 40 equals t. So negative 32 t equals negative 40. T equals positive 1.25 seconds. So our velocity is equal to 0 at 1.25 seconds. Now what do you think this means? Okay. Coming back up to our picture, notice that our velocity is going to be positive until we get to the top, and then at the top it's going to switch to negative when it starts going back down. At the top, notice we're also going to be flat, which means we have a slope of 0. Okay. Plus, if your slope is going to be positive and then switch to negative, at some point it has to go through 0. So when we have a slope of 0, that's always going to be at the top. Okay. So what does this mean? This means that the ball will reach maximum height and start falling down at 1.25 seconds. Which is kind of cool. So again, to find that top, you say, well, where would my slope be equal to 0? Or in this case, our slope, or our first derivative, is our velocity. And finally, when does the ball hit the ground? So that would be saying when. So when is the ball hitting the ground? That's talking about the actual height. So we want to deal with height. So when is our height equal to 0? So we take our height equation and set equal to 0. So negative 16 t squared, 40t 6. I've already checked. You can't factor this one, so you do need to use the quadratic equation. Of x equals plus, I haven't done this for a really long time, negative b plus or minus the square root of b squared minus 4ac all over 2a. So a, b, c. So negative 40 plus or minus the square root b squared 40 squared minus 4 times negative 16 times 6 all over 2 times negative 16, which equals, so it equals 2.64 or negative 0.14. Now again, if you come back up and look, so this root would be our negative 0.14. This root would be our 2.64. Now this is negative time. That doesn't really mean anything to us. We're going to go with the positive one because we threw it up at 6 feet. It goes up and then down to hit the ground, so it must be at that 2.64 seconds. So the ball will hit the ground at 2.64 seconds. Okay, and one more application for slope, which truly isn't anything new. It's just what we've been doing over and over, but we like to, apparently in this class, introduce lots of formulas. Or, as I like to do, just remember the concepts instead of new formulas. Okay. But this one is, if our derivative at point x equals a is f prime of a, okay, we know that at x equals a, if x goes up by 1, then y should go up by about our slope, or our derivative. So this is just our basic definition of slope. And I've written things like this quite a few times in the videos. So this also means, so we said if x goes up by 1, then y goes up by our slope. Well, that means then if x should go up by h, then y should go up by h times f prime of a. So this means if x goes up by 2, y should go up by 2 times our slope, right? Or if x goes up by 3, y should go up by 3 times f prime of a. That makes sense, right? And so that's why they have this nice little formula. So if x goes up by h, y goes up by about h times f prime of a. So let's see what this means for us then. So liquid is pouring into a large vat. At time t hours, there are 5t plus square root t gallons in the vat. At what rate is the liquid flowing into the vat at 4 hours? So this means we need to find the derivative. They didn't actually say if this was f or g or whatever, so let's just say that this is f of t. So then let's find the derivative, f prime of t. So derivative of 5t would be 5 plus the derivative of square root of t. So f of t equals 5t plus square root of t. Or you could rewrite that as 5t plus t to the power of 1/2. So we took the derivative of 5t is just 5, but the t to the 1/2, we're going to have to bring down the 1/2 power, take our t, and drop the power by 1, so to negative 1/2. Or this is 5 plus 1 over 2. Negative means take it down the bottom, and 1/2 means the square root. So there's our derivative. Let's see what that would be at 4 hours. So it's going to be 5 plus 1 over 2 times the square root of 4. So 5 plus 1/4 for 5 1/4 gallons per hour. So this is, we can say at t equals 4 hours, if we increase by 1 hour, we expect to get about 5.25 more gallons. Alright, so if x goes up 1, y goes up about that much. But in our next question, it says from 4 to 4.3 hours, how much liquid should have flowed into the vat? So from 4 to 4.3 hours, this means we want to go up by just 0.3 hours. We don't want to go up 1 whole hour, we only want to go up 0.3 hours. So how are we going to figure out how much more water should have flown into it? Well, you just do 0.3 times your slope. So 0.3 times whatever our slope was, or 0.3 times 5.25 equals 11.825 gallons. Oops. I didn't type that in my calculator correctly. I didn't clear out what was already in there. 0.3 times 5.25 is 1.575 gallons. Okay, so again, if we increase by 1 hour, we expect to go up by 5.25 gallons. But if we only increase by 0.3 hours, we do 0.3 times 5.25, so we should only go up by about 1.5 gallons. Now, just as a final note, make sure you're reading all the examples in this section. There are many types of application problems. I'm not going to cover all of them in videos because there are, again, so many, but our textbook is pretty good in their actual application problems. Sometimes all of the theorems get to be too much, but the application problems are pretty good to read in the textbook. So make sure you're reading all the examples. You only get good at story problems applications by seeing lots of examples.